Hello everyone, I am Dr. Sirajul Faisi. I welcome you in my YouTube channel. Today in this video, I am going to talk about electronic spectra of coordination compounds. So, what is UV visible spectra? You can see here. This type of graph is come from UV visible. What is UV and what is visible? Ultraviolet and visible spectra of transition metal complexes. Shows the transitions of the electrons. Analysis of these spectra can be quite complex. You can see titanium, vanadium, chromium, and different oxidation state of chromium. Manganese, you can see manganese, and if you compare manganese spectra with titanium, you can easily identify the compound contains manganese or titanium. You can see the vanadium, very clear pictures. Then height, you can see this one and this one, very different. Now you can see this one and this one, this one and this one. So copper one, you can see little bit hump, not sharp. Here is very sharp. This one you can sharp, but this peak you can see it is not sharp. This peak very sharp. Now again you can see here is also not very sharp. Here too much. Here this peak. So this peak also. So if you see the peak, you will find, and accordingly you can analyze your UV visible spectra. Now, UV visible spectra are used to determine the value of delta naught. You know delta naught for the complex. The spectra arise from the electronic transition between T2G and Ag set of molecular orbital. Electron-electron interaction can greatly complicate the spectrum. Only in case of single electron is interpretation of the spectrum straightforward. So, titanium 3 plus D1 is 1 electron systems. Now you can see this peak is also not here. You can see this way and this way. So it is look like a ham. So D1 configuration only a single peak is seen. It results from the electron promotions from T2G orbital to Ag orbital. The toothed appearance of peak is due to the Jahn-Taylor distortion of the excited state. The energy of the peak delta. So you can see it is not sharp, it is like toothed. It means there is a further phenomenon happening in transition state, and that is the Jahn-Taylor distortion. Now general observation, D1, D4, D6 and D9 usually have one absorption through a side hump. Hump is like this. Results from Jahn-Taylor distortion. So you can see little bit hump, you can see little bit hump, this is little bit hump. This is not a sharp. So general observation D2, D3, D8 and D7 usually have three absorption. One is often obscured by a charge transfer band. So you can see 1, 2, 3, 1, 2, here 1, 1, 2, 3, 1, 2. So here is 3 is clear, but again there is a hump. This is very nice. This 2 is very nice, but there is a hump. Now general observation D5 consists of very big, relatively sharp transition which are spin forbidden and a very low intensity. You can see intensity is very low, or there is no sharp peak. Now, qualitative explanation. Considering chromium 3 complex such as chromium NH3 whole 6 3 plus, the ground state configuration is the transitions from the dxy to dx square y square or dyz or dx to the dz square orbital involve a relatively minor change in the environment. So dxy, dyz, dxz, dx square and dx square minus y square. You have 3 unpaired electron here, dxy, dyz and dxz. Now qualitative explanation. The transition from dxz and orbital to dz square will involve a relatively minor change in the electronic environment. So considering chromium 3 complex such as chromium NH3 whole 6 3 plus, the ground state configuration is like this. The transition from dxy to dz square or dyz at dx to the dx square minus y square orbital involve a major change in environment. So you can see here the transition from orbital in the xy plane to the dz square orbital involve a fairly major change in the electronic environment. So, since the promotion of an electron from the T2G set of orbital to the EG set can involve differing change in the environment, several peaks will be seen in the spectrum. So, you can see here, this is a charge transfer, and then you can see this and this one is T2G and A2G, T1G, T2G, and total T2G, T2G, and you see this one is very important, this magnified absorption EG to A2G. So A2G 4 and EG doublet. We call it doublet, this is quad. So how to read this one is y-axis log epsilon L per mole, liter per mole per centimeter, and this one is 50,000 centimeter inverse lambda nanometer. So you can change nanometer to centimeter inverse, and this is the magnified absorptions EG. So doublet EG and quartet A2G. Now spin forbidden transitions. Hello everyone. Now I am going to show you spin forbidden transition. You know Mn2 plus and Fe3 plus usually have a high spin D5 configuration. As a result, all electronic transitions are spin forbidden. Mn2 compounds are sometimes a very pale pink and Fe3 compounds a very pale green due to relaxing of the selection rules. Now friends, Tanabe-Sugano diagram. What is Tanabe-Sugano diagram? In order to accurately interpret the electronic spectra of transition metal complexes, a series of diagrams have been created, and these diagrams are used to assign transitions, initial energy state and final energy state, to peak observed in the spectra, and to calculate the value of del naught. Now, Tanabe-Sugano diagram have the lowest energy state, the ground state, plotted along the horizontal axis. The energy of excited state can then be readily compared to the ground state. So, this is the Tanabe-Sugano diagram. Now you can see the energy level T1, T2, E, so many, and then a starting point you can see, and then splitting with different value. So many tables eliminates or use dotted line for excited state, and that are spin forbidden. That is dotted one. Now also, since d orbitals are all G-ready and G script is usually left off, so you can see there is no G term here. So the vertical axis is E by B. This one y-axis E by B, where B is a Raka parameter and B is a measure of repulsion between terms of the same multiplicity. Now X, this one, the horizontal axis is del naught by B. In order to determine del naught, we need to determine the value of B or mathematically eliminate it. Now, the diagram for configuration D4 and D7 or D4 to D7 have a vertical break. You can see this break, vertical break, in the middle of the diagrams. This is the middle of. This is due to the shift from high spin weak field complex to low spin high field complex. Now, symmetry levels and electronic configuration. You know, as far as right side of the diagram at an infinitely strong octahedral field, the symmetry level correspond to the electron configurations of the complex. T designs a triplet generates a symmetrically occupied state. So, 1 electrons here, 1, 2, 3, 4, 5, 6, 7 electrons. Now, an E level diagram, a doublet generates a symmetrically occupied state. You can see this. And A and B level designates a non-degenerate state like this. So, interpretation of spectra D1 and D9. There is only one spin allowed transition with the energy absorbed equal to the value of delta naught. So, this is the here one transition, here one transition, D1 and D9 system. Now, interpretation of spectra D1 and D9. D1 excited state exhibit a strong Jahn-Taylor distortion, as is seen in the UV visible spectra. It should be sharp, but there is a hump due to Jahn-Taylor distortion. Now, D9 system also have side peak, and in D9 the state exhibit a strong Jahn-Taylor distortion. The result is a side peak in the UV visible spectra. Now, interpretation of spectra D4 and D6 high spin. The Tanabe-Sugano diagrams show only one spin allowed transition for either complex. The frequency of the absorption is equal del naught. So, D4 high spin, D6 high spin. You can see this is x-axis, y-axis, x-axis, y-axis, E by B, del naught by B. Now, interpretation of spectra D4 and D6 high spin. The single peak show absorption distortion from octahedral geometry due to Jahn-Taylor effect. So, chromium 2 plus D4, Fe2 plus D6. So, my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.